Well, in this video, we're going to talk about Williamson ether synthesis, and it's the idea of just creating ethers from some sort of alcohol in a non-nucleophilic base with some sort of alkyl halide, where your alkyl halide prefers SN2 chemistry, SN2 like chemistry. So SN1, E1, E2 will not work for these chemistries. So you want to make sure you're getting SN2 chemistry for these. So let's get straight into the thick of things here. So we have methanol here, and we're reacting it with this. Now, typically for Williamson ether synthesis, you'll see this base here, sodium hydride. And it's a non-nucleophilic base, which is just some sort of H minus. So what it actually does is that it actually deprotonates your oxygen, deprotonates your oxygen, right, to give you something that looks like this. And again, in this video, I'm not going to worry about the mechanism. We already talked about the mechanisms of Williamson ether synthesis. But essentially, it takes off, it deprotonates your oxygen and gives you something that now becomes a nucleophile, which is what we talked about here with the alkoxide. So what this does is that it attacks your carbon that's containing your leaving group and dispels your leaving group. So this is the product that we get. Yeah, we get or CH3 here with their O in the middle bonded to this ethyl group here. So this is the product we get, and this is the general form of just creating ethers. So let's look at another one. So there should be a cyclohexane ring, benzene ring. All right, and we're gonna add this reagent to it and sodium hydride. So the first thing is going to happen, non-nucleophilic base deprotonates my oxygen, right, to give it a negative charge. So I have my bromine here, plus my now alkoxide. Right, so all this is going to do is attack and kick off the bromine. Right, and this should be going to this carbon here. Sorry about that, guys. That should be going to that carbon there, and this is what we make. Right. So this is our product and what we make. Again, so notice that my oxygen is bonded to this carbon that contains this isopropyl group here. So this is the product that we get. So again, nothing hard. So let's look at some more examples. So you have this OH here plus this iodide here, and we add sodium hydride, our powerful non-nucleophilic base. All right. So again, my oxygen gets deprotonated, and this is what I make. So my oxygen gets deprotonated, and this is what I make. Again, oxygen gets deprotonated, nucleophile attacks my carbon, it's containing my iodide, displaces my iodide, and this will be the product that I get. All right. So let's look at another example. So what if we added ethyl bromide, this ethyl bromide group here, plus this OH here, all right, and sodium hydride? What would be the product? Well, again, hopefully you'll notice that my oxygen will get deprotonated, and this will serve as my nucleophile. So with that being served as my nucleophile, that means my product has to look something like this. We have an O. We have a phenyl ring that's bonded to a bromine, that's bonded to a carbon. This bromine gets displaced. So this now is bonded. All right, so that bromine gets displaced. Right, our oxygen would replace that bromine, would replace this carbon here. Right, so putting everything together, we get this carbon that is bonded to an oxygen, right? And that oxygen has this whole entire top group on it. So if we could draw that in such a sense, I'm going to draw it linearly where I have this oxygen coming down this bond here. So I see that I have an ethyl group, a methyl group going this way, and I have 1, 2. Right. So that will be my product. So these reactions are actually not, really difficult at all. Again, they're not really difficult at all. But something that is very important. Remember we said that we need SN1 or SN2 like chemistry. So maybe we should point something out here. So maybe if I gave you maybe an instructor gave you this on an exam, right? And you decide to add methanol. All right. And sodium hydride. What would be your product? Well, notice that sodium hydride will actually deprotonate my oxygen. And now I have something that is very basic. Well, will this give me SN2 chemistry? The answer is no. This will not give me SN2 chemistry. And actually the product of this will look something like this. This will be the product of this reaction. This is not good. If we want to create ethers, we need some sort of SN2 like chemistry, which means, and this favors this, the SN2 chemistry typically favors alkyl halides with primary secondary carbons with leaving groups, right? Primary secondary carbons. So again, be very careful. This is very basic, but I have a tertiary alkyl halide here. So this nucleophile could never attack this tertiary alkyl. It's just steric hindrance is just over the top here. So what will actually happen is that we have these two hydrogens. It will actually grab a hydrogen and then kicks off to form this double bond, and then the bromine kicks off to give my alkene. Now this is my more substituted product, so this is my Zaitsev product. But again, hopefully you could see that these hydrogens here could also be displaced, and that will give me my Hoffman product. All right, so be very careful. So that's why we say when we talk about Williamson ether synthesis, we look at SN2 like chemistry. Now, here's something that you should keep in mind. Anytime you could form 5, 6, 7 membered ring, do it. All right. Anytime you could form 5, 6, or 7 membered ring, you need to do it. So what do I mean? Well, okay, let's see. If we what if we had this molecule here, all right? All right, and we decided to add sodium hydride. What will be the product? Well, again, hopefully you'll see that my oxygen gets deprotonated. Right, my oxygen gets deprotonated, and I have an alkyl halide on the same chain. So this is actually going to react with itself. Now let's see how many carbons we're actually going to find. Right, so if I count my because I'm thinking this is going to form a ring because I have something more than 5 here. So let's see, I have 1, 2, 3, 4, 5. So I see that I can form a 5-membered ring here. So with that being said, the product for this reaction will look something like this, right? This comes in attack and displaces my iodide, right? So let's draw this carefully. We have this oxygen that's bonded on the top. We have carbon 1. We have carbon 1, 2. So let's see, we have 1, 2, 3, 4, 5. Right, we have 1, 2, 3, 4, 5, and then the only thing that left is just this. So let's count how many members are in our ring. 1, 2, 3, 4, 5, which is exactly what we saw the first time. So again, anytime we could form 5 or 6 membered ring, do it. So maybe, let's see what examples I have here. So maybe if I were to give you something like this again, all right, so maybe I gave you this example and you were to add sodium hydride, what will be the product? Well, again, I see that I could form a 5, 6, or 7 membered ring. And the reason why, if you could do it, is because it's simply more stable. So again, I see that I have, let's count our carbons. So we have 1, 2, 3, 4, 5, 6. Yes. So you know that somehow, some way, this has to be a 6-membered ring. So again, when I deprotonate, I'm going to have my oxygen that's negatively charged. And this is going to simply attack the carbon containing the leaving group and expel the leaving group. So again, the product for this reaction will be, let's count. Well, again, we have an oxygen down here, right? So let's see, this is 1, 2, 3. So we have 3 out of the 5 so far, right? Out of the 6 so far, right? That makes 4. This makes 5. This makes 6. And then we just connect the bond here. So again, let's see, we have 1, 2, 3, 4, 5, 6. 6-member ring indeed. All right, so anytime you could form 5, 6, or 7-membered rings, do it. Okay, and this is essentially just the reactions of Williamson ether synthesis. Not very complicated. You just need to remember these typically do not react in strong bases. So again, and let me kind of put emphasis on this. Sodium hydride is actually a non-nucleophilic base, so it's some sort of H minus. So it's not something along the lines of like sodium hydroxide, which is straight nucleophilic. So that will give you attack. But again, that is not possible since your oxygen needs protonation, right? So that will not be possible. Maybe if I have this molecule here and I react it with sodium hydroxide, I will not get any reaction. Again, simply because this needs protonation and there's no source of hydrogens in this solution.